So far in our discussion of molecular orbital theory, we've worked only with linear molecules. What I want to do in this video is talk about how you would extend that to something that's not just along a line, but exists in a plane. The molecule I want to use as an example is borane, BH3, because it'll be simpler to have the outer ligands be hydrogen. Matter of fact, I'm not going to do any examples for you that don't have hydrogen as the outer ligands, because it gets really messy when the outer atoms that are in the ligand group have more than one orbital each and have orbitals with different symmetry. The Lewis structure for borane that you would probably draw if I asked you to draw a Lewis structure for borane would have single bonds between each boron and hydrogen, approximately 120 degree, well, exactly 120 degree bond angles. I'm not sure I'll achieve that here. And sp2 hybrid, if you're talking about valence bond theory, because you have 3 electron groups and a trigonal planar molecular geometry. So if you were to use a valence bond theory, approach to the orbital picture, you would create 3 sp2 hybrid orbitals, pointing out with intraorbital angles of 120 degrees. Often we don't even bother showing a little tiny back lobe of those sp2 hybrid orbitals, and these are formed from the 2s orbital, the 2px orbital, and the 2py orbital. And it's sp2, right? 2 of the 3 p orbitals combined with the s orbitals to form 3 new sp2 hybrid orbitals. And then each of those sp2 hybrid orbitals would overlap constructively or destructively with one of the hydrogen 1s orbitals. So you would get 3 identical bonds, each formed by overlapping one of the hydrogen 1s orbitals with one of the sp2 hybrid orbitals on the central boron to form 3 sigma symmetry bonds. And you would incorrectly, as it turns out, predict that all 6 of those electrons in those bonding orbitals would have the same energy. That's no more true for borane than it was for beryllium hydride, which means that the valence bond theory has, again, localized my sigma bonding electrons too much. The 2py orbital and the 2px orbital are used in forming the hybrids. There's still a 2pz orbital that has not been used, and so in addition, boron would have an unhybridized empty 2pz orbital, which we would simply rename pi z because it has pi symmetry, and now it's a molecular orbital instead of an atomic orbital. We changed from the Arabic, from the English alphabet to the Greek alphabet. Usually when you're doing a valence bond theory picture, and I think in our textbook, it only shows the bonding orbitals and doesn't show the antibonding orbitals. But in principle, there is an antibonding orbital as well. We know that for borane, we have to get 7 total molecular orbitals. Because there are 7 atomic orbitals, 4 from boron and 3 1s orbitals from hydrogen, and we always have to have the same number of molecular orbitals that we started with atomic orbitals. So doing the valence bond theory, we created 3 new bonding sigma orbitals from constructed overlap of sp2 hybrids with 1s orbitals. We have the empty pi z orbital, the old pz orbital that's not interacting. In order to not break this rule, we have to have 3 equivalent anti-bonding orbitals where the sp2 hybrid interacts destructively with the hydrogen 1s orbital. Right? Where the sp2 hybrid interacts destructively with the hydrogen 1s orbital. Right? We have the negative sign here, so this would be destructive. So valence theory we know doesn't really work because it localizes the electrons too much and predicts incorrectly that all of the bonding electrons have the same energy. How can we get a better looking picture using electroorbital theory? And once again, we're going to turn to ligand group orbitals. But now we'll have to have 3 of them. Because there are 3 hydrogens, each of which brings one s orbital with them. The simplest situation is always to have everybody in phase. We're going to call that lambda 1. All 3 hydrogen 1s orbitals have the same sign on their wave function. That's the only way we can create a ligand group orbital that has 0 nodes. In the case of beryllium hydride, there was only one other orbital we could create that had a single node bisecting the molecule. But now that we're working with a planar molecule instead of a linear molecule, there's more than one way that we can cut that in half. You can only cut a string in half one way, but you can cut a piece of paper in half twice, 2 ways. And if you went to a 3-dimensional molecule, there'd be 3 ways to have a single node, because you can cut a cube in half 3 different ways. One way we can cut it in half would be to cut it on the horizontal plane and have the top lobe be out of phase, the top 1s orbital be out of phase with the 2 1s orbitals on the bottom. We'll call that lambda 2. So what's the other way to put a single node through? Well, we can slice it here, but that would create exactly the same symmetry orbital. It would just be rotated 120 degrees. We can slice it here, rotated 120 degrees. When you're creating 2 degenerate orbitals, each of which has 1 node, it's best to make those nodes perpendicular to each other. If we do that, then we want our 3rd ligand group orbital, lambda 3, to have a node on the vertical plane, which means that the 2 lower hydrogen 1s orbitals will be out of phase with one another. But it means that the node goes straight through the center of the other hydrogen. And what that means is that this 1s orbital makes no contribution to the ligand group. In other words, the coefficient in front of that wave function is 0. So lambda 3 is some coefficient times psi 1s for hydrogen A, hydrogen A, and some contribution, but out of phase, for the 1s orbital on hydrogen B, plus 0 times 1s orbital from hydrogen C. So that makes no contribution, and we only have contributions from hydrogen A and hydrogen B. Lambda 1 is equal to some coefficient times psi 1s A plus some coefficient times psi 1s B plus some coefficient times psi 1s C. And lambda 2 is equal to some coefficient times psi 1s A plus some coefficient times psi 1s B minus some coefficient times psi 1s C. So these 2 are in phase, but they're out of phase to the 1s orbital on hydrogen C. We've now created those 3 ligand group orbitals. These 2 are degenerate because they each have 1 node, and orbitals with the same number of nodes and have the same energy. So if we were to look at our ligand group orbitals on an energy diagram, we started with the 3 hydrogen 1s orbitals, and we created from that 3 ligand group orbitals, lambda 1, lambda 2, and lambda 3. Because there are 2 orbitals that are above where the 1s orbitals were in energy, and only 1 below, if that distance is x, this distance has to be 2x. So lambda 1 will be lower in energy by twice the distance, as lambda 2 and lambda 3 will be above. Ligand group orbitals don't exist any more than hybrid orbitals do. But if we wanted to, we could imagine having now taken these 3 hydrogen 1s orbitals and created from them, temporarily anyway, a filled lambda 1 orbital and half-filled lambda 2 with an empty lambda 3. So now what we have to do is figure out how to take the beryllium, the boron orbitals and interact them with the ligand group orbitals. And we will be greatly aided in that task by symmetry. So we know that we have a 2s orbital on boron. We have a 2px orbital on boron. We have a 2py orbital on boron. And these kind of called lousy others. And we have a 2pz orbital on boron. The 2pz orbital does not lie in the plane of the molecule. In fact, it has a node at z equals 0, which is the xy plane. All of the atoms lie in the xy plane. None of the other orbitals lie outside the xy plane. Right? All of these lie in the xy plane. So this will again just become pi z. And it's a non-bonding orbital. It doesn't change in energy, it doesn't change in shape. Pi z is in fact just the 2pz orbital from boron. That's the same as it would be in the valence bond picture. So we have 3 boron atomic orbitals, and we have 3 ligand group orbitals. But we know that orbitals can only interact with other orbitals with the same symmetry. So if we can find ligand group orbitals that match the symmetry of the boron atomic orbitals, then we, and in fact only the 2s orbital has the same symmetry as lambda 1. So we'll end up creating 2 new orbitals, lambda 1 plus and minus the 2s orbital. No matter what plane you reflect through, you don't have any change in the sign on the wave function. That's true for the 2s orbital, which is spherically symmetrical, and of lambda 1. The 2px orbital has a node at x equals 0, which is the yz plane. And that's the same place that we have the node here. Which means that lambda 3 can only interact with the 2px orbital and not with either of the other 2. So that's 2 more combinations. And conveniently, 2py has a node at y equals 0, which is the xz plane. And that's exactly the same place as the node is on lambda 2. So our final 2 combinations will be lambda 2 plus and minus the 2py orbital. So it was really nice when we created our ligand group orbitals that we conveniently created 3 different ligand group orbitals that match the symmetry of the 3 in-plane atomic orbitals on boron that we need to combine them with. Right? One had the same symmetry as 2s, one had the same symmetry as 2px, and one had the same symmetry as 2py. By creating those 3 ligand group orbitals with 3 unique symmetries, we now allow ourselves to create our molecular orbitals by only adding or subtracting 2 orbitals at a time. 2 orbitals at a time we can handle. In the case when we have 3 orbitals, we can handle it because 2 of the combinations turned out to be degenerate. But when there's 2 orbitals, we don't even have to worry about that. So what do these look like? All right, let's take them one at a time. So lambda 1 plus the 2s will look like that. The inner lobe, again, doesn't really matter. We're going to have constructive overlap and bulging, and we will have, as usual, an orbital that can extend over all 4 nuclei with no change in sign, that allows those 2 lowest energy electrons to delocalize over all 4 nuclei. Should be symmetrical, not very good that way. So it's a bonding orbital with respect to all 3 of the boron hydrogen bonds. This is what valence bond theory cannot account for. The lowest energy electrons that interact with all the nuclei simultaneously. Valence bond theory always always localizes the electrons in one bond between 2 atoms rather than multiple atoms like this. Pi orbital delocalization is possible in valence bond theory, but single orbital delocalization is not. So that's lambda 1 plus 2s. Lambda 1 minus 2s changes the sign on the 2s orbital and creates sections where new nodes are created. In fact, in this case, the node that's created is going to be a spherical node. Which is much like the spherical node that's there in the 2s orbital in the first place. And it will be anti-bonding with respect to all 3 of the boron hydrogen bonds. So this is molecular orbital number 1. We know that's the lowest energy orbital. This one turns out to be molecular orbital number 5. I'll explain why that's true later. So those are the 2 possible combinations of lambda 1 with the 2s orbital. Now let's look at the possible combinations of lambda 2 with the 2py. Those are the ones that have the y equals 0 and the xz plane as the node. So we get a bonding interaction. So we actually have some constructive overlap here for sure. And we probably have a little bit of constructive overlap here as well. Right? It's going to be less strong, but we do have it. And the resulting orbital will look like this. So it too is bonding with respect to all 3 of the boron hydrogen bond. But it's higher in energy than molecular orbital number 1 because it has a node that goes through the center of the boron. So that's molecular orbital number 2. We can also have lambda 2 minus 2py. So the 2py orbital will change sign. Creating new nodes. In all of the locations. There'll be a little bit of constructive overlap here, though. because those hydrogen 1s orbitals may reach out enough to interact with the top lobe of the 2p orbital. So what that's going to look like is little lobes here. Little lobe here, an orbital that kind of extends around both the hydrogens. So our node is parabolic. There are two parabolas as nodes. And this is going to be MO number 6. Just one spherical node here, two parabolic nodes here, so MO number 6 would be expected to be a little bit higher in energy than MO number 5. That should make sense anyway, because MO number 5 was formed from lambda 1, which is the lowest energy of the Ligand group orbitals, and 2s, which is the lowest energy of the valence orbitals on boron. This molecular orbital number 6 was formed from a higher energy Ligand group orbital, lambda 2, which had a node, and a higher energy atomic orbital, because the 2p subshell is higher in energy for boron than the 2s subshell. So if the two atomic orbitals that form it are both higher energy than the two that form the other one, the resulting combination would be predicted to be higher in energy. This looks like a little bit like a guy standing on his head. He's got his head here and he's using his hands to brace himself. And if you flip it upside down, it looks like a little robot. Finally, we need to look at 2px overlapping with lambda 3. So we'll have lambda 3 plus 2px, and we'll have lambda 3 minus 2px. Here we've got constructive overlap. Two locations, so the resulting orbital, although it's not bonding with respect to hydrogen C, is bonding with respect to both hydrogen B and hydrogen A. So it's a bonding orbital. It has a single node, as does molecular orbital number 2, which means that molecular orbital number 3 should be degenerate with molecular orbital number 2. And that'll also make sense if you consider that lambda 2 is degenerate with lambda 3, and the 2py orbital is degenerate with 2px. So if you're forming it from a combination of two orbitals that have identical energy, you would expect that the result would also have identical energy. Molecular orbital number 7 should be degenerate with molecular orbital number 6 for the same reason. Lambda 3 and lambda 2 are degenerate. The 2py orbital is degenerate with the 2px orbital. So the destructive combination of those ought to give an orbital with the same energy. What does that look like? Well, that looks like this. There are new nodes being formed there. And of course, we already have the existing node. So it looks a little bit like a pi anti-bonding orbital, but it's not quite the same as the stretched closely we would normally expect. It's not symmetrical because these two lobes are closer to the boron than these two lobes are closer to the center. And then there's a new node here, and a new node here, two nodes that are perpendicular to each other, two parabolic nodes. Often orbitals with the same number of nodes will have the same energy. And so to know what great surprise, MO number 7 and MO number 6 are degenerate to one another. So that's what they look like. MO number 1 delocalized over all of the atoms. MO number 2, right? These electrons are also delocalized over all the atoms, but they can't be here. They can't be on the, the XZ plane. MO number 3, bonding with respect to hydrogen A and B, just non-bonding with respect to hydrogen C, can't be on the YZ plane. And then MO number 4 with its spherical node, MO number 6 with its parabolic node, and MO number 7 with its two kind of planar nodes. And in the middle, we still have molecular orbital number 4, which is the IZ, non-bonding orbital. Let's put that all together on an energy diagram. And what we would start with is the boron 2s and px, py, and pz orbitals, and our 3 hydrogen 1s orbitals. And when we're done, we have pi z. We have MO number 1 way down here. And we have MO number 2 and 3. A little higher in energy. And then we have MO number 4. And MO number 5. MO number 6. I'm not sure how well I've done at getting that multi-atomic orbital energies, and the sum of the molecular orbital energies is identical. One key thing is the molecular orbital number 1 is much lower in energy relative to the original orbital energy levels than any of the others, because of the ability of electrons to localize over all the nuclei and spend a lot of time where they're interacting with more than one nucleus at a time. Here is the 7 orbitals. This is the 5. All right. I forgot to label pi z. Pi z is number 4. pH3 has 6 electrons. We'll fill the 3 low energy molecular orbitals. The bonding orbitals, our frontier is here. Where the LUMO is the pi z orbital. A nucleophile that wants to donate its pair of electrons will donate it to this non-bonding pi orbital, which I'll bond boron, which makes sense because boron is the element that has the unfilled octet and therefore should be electron deficient and act as a Lewis acid. And our HOMO is the degenerate pair of MO2 and MO3, which has most of its electron density on the hydrogens and not on boron, which makes sense because hydrogen is a little bit more electronegative than boron, so the hydrogens will have a partial positive charge on them. The dipoles will lie, sorry, a partial negative charge on them. The dipoles will all lie like this. There's not much electronegativity difference. Hydrogen 2.1 to 2.2, boron's 2. But there is a little bit of a delta minus on hydrogen, a little bit of a delta plus on boron, which means that if you are an electrophile, you're going to interact with the hydrogens. If you're a nucleophile, you're going to interact with boron. And that's consistent with what we know here, because the electrons in the HOMO are mostly on hydrogen, and the orbital on the LUMO that's empty is mostly on boron. So that's a planar molecule. The new thing that we introduced here that you didn't know before is that it is possible to have a node that goes through the center of an s orbital, and that causes that s orbital to simply not make a contribution to that bigger group. We can do the same thing in other systems.